So welcome to lesson 2 of topic 5, solids, liquids and gases. Today we're going to look at pressure, and we're going to talk about how pressure works, and we're going to talk about how we can use the formula for pressure. But I thought we'd start off by watching a short, it's about 2 minutes video of pressure in action.
Zo, kijk, je ziet hem zakken, je ziet het beekje, kijk.
Ja! Wat een guys!
Je krijgt echt geen geld hoor. Jongen!
Zwemmen! Ik heb...
Ja. En dit laat ik aan jouw ouders zien. Ja. Woe!
Heel wat tijd voor over, hè?
Lekker!
Je gaat niet redden.
Oh, die pen is best. Voor je. Deze, ja.
So if there's a normal lesson, we'd talk about how we'd rescue somebody who fell through the ice if we didn't have any ropes or anything. And of course the best way to do that is to spread yourself on the ground, on the ice, and crawl along. Because you're taking your force, your weight, don't forget, and you're spreading it over a bigger area to reduce the pressure. So the pressure on the ice depends on two things. It obviously depends on your weight, but it also depends on the area that your weight is spread over. So we'll look at some examples where that happened. So camels, we're in the right place for camels, have very large feet. And of course that's because they're heavy, so we can spread their weight over a bigger area so there's less pressure so the camel's feet don't sink in the sand. If camels had feet like antelopes, very small, they'd have the same weight but a smaller area, so a higher pressure. And of course their feet would sink in the sand. So camels are a good way of the way that nature has adapted and used the idea of pressure. Snowshoes are another idea. When I lived in Norway, we had some snowshoes. When it snowed there, the snow was very deep, maybe a metre deep, and very soft, so it was almost impossible to walk through. But snowshoes, of course, spread your weight over a bigger area, so it's possible to walk on top of the soft snow, and it's a good way of getting about. So again, we're using the idea of spreading our weight over a bigger area to reduce the pressure. In English, we call these caterpillar tracks, and the reason that large large road-moving vehicles or tanks have caterpillar tracks was if they had normal tyres, they'd probably sink into soft ground. So again, the caterpillar track is a way of taking the weight, spreading it over a big area so there's less pressure. So the tank or whatever the vehicle is less likely to sink into soft ground. This is also true of house foundations. I used to live in Houston. Houston is built on marsh, so the ground is very soft. So they build a big concrete slab that they place a house on. And that just basically spreads the weight of the house over a bigger area, so the house is less likely to subside or to sink into the soil if the soil is very soft. Obviously, if you live on rocky ground, you don't have to worry about that so much. But in Houston, the houses were on big concrete slabs, which spread the weight of the house over a bigger area. And finally, this is an example actually from my house when I used to live in Poland, in Warsaw. We had this metal sofa, and it used to dig in and spoil the wooden floor. So, of course, just by putting a stiff piece of cardboard underneath it helped to spread that pressure, and it didn't cut into the floor so much. Okay, so I want to tell you about a dream I had last night about some of my students. The dream was one about one of my most annoying students. I won't say who it was, and I finally snapped in the class. So I grabbed a board pen like the one on the left, and I tried to stab him. And he was screaming, and the class were trying to pull me off him. But of course I wasn't killing him, because the pen, it was hurting him as I tried to stab him, but it didn't go in. And then I reached to the desk and found a ballpoint pen. And I reached, and of course I continued to stab him with a ballpoint pen in the side of the neck. And of course it went in, and there was blood all over the place and people screaming. And he died in the dream. There's a film called Casino with Joe Pesci, where he plays a gangster, and he does this to a guy in a bar. He stabs him to death with a ballpoint pen. Now, of course, I was able to stab him with a ballpoint pen instead of the board pen, because the ballpoint pen has a very small area. So even though I'm using the same force, the smaller area means that there's a higher pressure. So when we say something is sharp, like this scalpel in the picture, what we actually mean is it's got a very small surface area. Yeah, so for the same force, the small area means a higher pressure. And in fact, a good surgical scalpel, the surgeon doesn't even have to press on. The weight of the scalpel is enough to cause the pressure to break the skin. Now, of course, the drawing pin uses it on both sides. So where you put your thumb, okay, you've got a big area there, so there's not enough pressure for the pin to go in your thumb. But if you look at the pointed end, of course, that's got a very small area. So your force on the drawing pin, that's enough pressure to actually push it into wood. When you think about it, this is a very clever object, yeah? So we're deliberately making the pressure small on one side so you don't hurt your thumb, but big on the other side, so the drawing pin will actually even go into wood. It's possible to push these into wood, which, when you think about it, is pretty amazing. Okay, so I used to make memes or memes about physics cat. This is my physics cat meme for pressure. So physics cat knows that pressure is force divided by area. So this brings us on to the formula we're going to use to calculate pressure. So here's another formula we've got to learn. Pressure is force divided by area. So you can see there, if the area is big, if you divide by a big number, the pressure is going to be smaller. And if the area is small, when you divide by a small number, you get a big number, so a high pressure. Now, of course, we measure force in newtons. We can measure area in meters squared, in which case the pressure is measured in newtons per meter squared, and we call that a Pascal. Okay, so if the force is in newtons and the area is in meters squared, the pressure is in newtons per meter squared, and we call that a Pascal. Now, we can, of course, measure the force in the area in centimetres squared, in which case the pressure would be newtons per centimetre squared. That is not a Pascal. It is a unit of pressure, newtons per centimetre squared, but that is not a Pascal. For it to be a Pascal, the area has to be measured in metres squared. Okay, so we're going to look at an example here. We've got Angelina on the left. She has a weight of 600 newtons. Don't forget, weight is measured in newtons. And the total area of her shoes is 150 centimetres squared, so that must be both shoes. Brad Pitt has a weight of 750 newtons. Don't forget, weight is in newtons. And the total area of his shoes is 360 centimetres squared. Men tend to have bigger feet than women. So let's calculate the pressure beneath their feet. Okay, so Angelina, pressure is force divided by area. Her weight, so that's the force on the ground, is 600. The area beneath her feet is 150. So the pressure beneath her is 4, so 600 divided by 150 is 4 newtons per centimetre squared. We've used centimetre squared, so they're not pascals. Whereas, of course, Brad, okay, force divided by area, 750 divided by 360, is actually less, 2.1 newtons per centimetre squared. So even though he has a bigger force, his feet are much bigger, so they've spread his force over a bigger area. So the pressure under Brad's feet is quite a lot less, almost half of what it is under Angelina's. So someone bought me a book a few years ago about bunny suicides. It's meant to be a funny book. So there's some slides here you can see different examples of the bunnies using pressure. Okay, so when this guy sits on the chair, yeah, his force is going to be directed on the forelegs of the chair. They've got very small area. There's going to be a high pressure. Obviously, it's going to crush the bunny's head. This is, of course, a guillotine. And then it's using the idea that the guillotine works because it has a very small surface area. So it's heavy, it has a small surface area, there's a high pressure under the blade. Of course, it's going to cut all the bunny's heads off and the man at the bottom. This is called a guillotine. It's a French word. So here's another example of a bunny suicide involving pressure. Those that hang from the ceiling are called stalactites. The ones on the floor are stalagmites. So that stalactite, the bunny waits there long enough, hundreds of years or whatever, will eventually fall off and kill the bunny because it's got a small surface area at the bottom. There's going to be a high pressure. Now, if this was a proper lesson, we'd now calculate the pressure beneath your own feet. So what we'd do is I'd get you to draw around your foot on a piece of paper, a piece of graph paper. You then count the number of squares. Count the number of squares to get the area under your foot. We get a balance to find your weight in newtons, and you can calculate the pressure beneath yourself. Yeah, so it's just a matter of finding the area under your feet. Like I say, we put our feet on squared paper, we'd count the number of squares under our feet, and so estimate the area under your feet, and use pressure is force divided by area to find the pressure under your feet. Now then, we'd also try and find the pressure under a car. So we go downstairs to the underground car park at school, and we'd find the pressure under my car. Now, I've done this lots of times in different schools. I'm just going to show you some pictures of when I did this with my car when I used to teach at the British School in Houston. So this was my car in Houston. I think it was some sort of Hyundai. That boy on the floor, I think his name was Cameron. He was from Scotland. So basically, we put some squared paper on the floor. I would carefully drive over the paper. The students would draw around the wheels, okay, to get the surface area of the wheels. Much bigger than you imagine, actually. The tyres squash a little bit, so the weight of the car is spread over quite a big area. Here you can see a little bit clearer how we did that. Yeah, so we put the graph paper, the squared paper on the floor. I very carefully drove over it in my car, and then the students drew around the shape. And like I say, it's much bigger than you'd expect. Of course, we then go back to the class and we do some calculations. So a car that size, a bit like a Land Cruiser, is probably 2 tons, 2,000 kilograms. So the weight then would be 20,000 newtons. We'd find the area under one tyre, and then of course we'd multiply that by 4, because there were 4 tyres, and then we calculate the pressure. To be honest, I don't know what the answer was. It's not too much. You might have in the past have had a car run over your foot, because the weight is spread over quite a big area with the 4 tyres. It sort of hurts, but normally it doesn't break your foot, if you're lucky. Okay, so you knew it was coming. There's a worksheet to go with this lesson where you're going to use that formula, pressure equals force divided by area. Don't forget, you might have to rearrange it as well. So force is pressure times area. Area is force divided by pressure, or whatever, using our triangle. Okay?